main speaker is not here yet. I volunteer to fill the gap. Oh, hey James, how are you?
I'm good.
So you decided not to make backup presentation today?
Yep, today.
That's fine. Well, actually, we came here to hear for the research update by Kevin, but this morning his research update was 2 slides long, and I've told that it is a little surprising, and maybe he got scared and decided not to come at all.
Oh, really?
Hey Kevin, how are you?
Hey, Professor.
Do you have updated slides, or you will show only those two?
Yeah, I only saw your email like a half an hour ago.
Do you have a computer with you?
No.
You can edit them on mine and add some text.
Okay.
I'll fill the gap and speak about something because the year will finish very quickly and
All right.
so there are no data, but you may at least add some verbal
Okay.
things. So do not listen to me. Prepare your stuff. So it's not in DSU, it's one of the grants opportunities, and for some of us it's just a pleasure and honor, and for some of us it is survival question. So there is a season of applying to proposals, and there are specific hints of what is expected, what is needed there. So some of the things that are requested by the different agencies, they migrate from one agency from another, and the goal of these hints is manifold. From point of view of agency or community, maybe the humankind needs new knowledge and fluff stuff like that. But from selfish point of view, I see it as a little pushing mechanism that brings me out of the comfort zone, and to look once again if we have in our methodology if we have perfect tools so we can improve them, and because applying to grants is necessary, and can we just blindly apply methods that we are already doing? Are they competitive, or they're missing something? So so the deadline is literally in a month from now, and some of them there is a list of open holes, and there are two things that are very new, very challenging, and induce the interest and necessity to improve and develop something. So one keyword is topological insulators, and I can share the slides, and it's all public materials. Nothing is from secret sources. So I have copy-pasted a couple of Google slides that I will show in maybe 15 minutes. And later we will discuss how, if the methodology that we are practicing can be applied to this code. They tell us some hints that one can look through and adjust. But before these new keywords, new materials are really throwing off. Like I saw them before and tried to leave them behind, not to look at them because they're scary, because they're new. And looking on these holes, I also was trying to avoid it, but since situation proves that some submissions are needed, so there are like whale semi-metals, terminology from different community. So this all comes to the umbrella of quantum materials, which there are no strict definitions, but it is the understanding is that by mixing together objects or interactions of known nature, one can observe some new unknown phenomena. It's concept of emergence. And among these quantum materials, primarily they mention topological insulators and graphene. So if we open the Wikipedia page on the graphene, or it will prompt to Dirac cone, and there is a suggestion, there is a prompt from this open public information, and even doesn't need to go deep into professional literature, that things that we are doing are cool for certain range of applicability, for molecules, for quantum dots, but if we want to jump into activity of these materials, there are things that are missed, that are not included or on the way to be included into the methodology that we all are practicing. So for this type of materials, it is critically important to include the momentum dispersion, the dependence of orbitals on momentum, and they are more rich than one-dimensional, more rich than nanowires. They're at least two-dimensional. So the main key feature, I was trying to do ugly hand drawing last time, but here is something from Pablo. So like this lower surface is HOMO, upper surface is LUMO, and the minima of the LUMO and maxima of HOMO do have discontinuity in the derivative. And later on, if we look through the text, it tells like in the vicinity of this Dirac cones, the carriers have zero mass. Zero mass, which it means that one can apply zero energy to accelerate them, so they will move freely. And it comes close to the concept of superconductor, when one doesn't apply energy to keep currents. And just in case, the kinetic energy is assumed as square of the momentum in regular free space. Right? Then the second derivative of the kinetic energy will be curvature of this parabola, and it will be 1 over mass. Right? So if it is a parabola, then it will be the second derivative always will be some finite number. But since here the shapes, they are not parabolic, they are cones, and in the point where they intersect, the second derivative will be infinite. So if the 1 over mass is infinity, then mass is 0. So if one learns how to utilize this feature of electronic structure, one can avoid losses. And it looks like one of the goals, to have the frictionless electronic transfer. So for the two-dimensional materials with Dirac cones are more simple to understand and more popular, but there are analogous features in the momentum dispersion for three-dimensional materials. I'm just telling what I was reading. It's not my area of expertise, but it's need. There is need to look there. And in case the features of the dispersion similar to Dirac cones are observed in three-dimensional things. And what are those features? The energy is not quadratic but linear in momentum, right? So for the cone, there is a constant slope of this dependence of energy on momentum. Same as for photons. Like for electrons, typically it's parabola, and for photons, massless particles, the dispersion is linear. So if there are three-dimensional linear relations between momentum and energy, it sounds from this article that it's called Weil material and Weil points. And also, I'm trying to look around what are the popular materials instead of graphene, molybdenum, sulfur, disulfide. So what are materials that show these features? Close your eyes and do not look. So Aaron is and Yevon are practicing spinners, and those are two-component spinners. But there is if one deals with, we are doing with electrons holes, and they all have energy about the same as visible photon. If one would look for energies like a couple million times bigger, like mega electron volts, then equations are somewhat similar, but instead of electron and hole, there will be electron and positron. They are coupled, and one uses combined object as analogous to spinor, but instead of two components, there are four. And those are it's Dirac equation for this for spinners, and there is some connection that I didn't study, so I just blindly copied. This looks very similar to Dirac equation, but probably if one looks carefully, it will be something different. So it's one spinner is and two spinners composing are entering into the four component object. And if one processes it further, one can find that dispersion will be not quadratic, the energy frequency not quadratic in momentum but linear. So if this feature is seen for electrons it's considered cool for today, fashionable. And there are some ideas how to use them. So I'll skip through a couple of the slides because it's very far. I look forward to study them. There is everyone tells about the concept of arc. So there is a way for charge carriers to migrate from one of this special point to another, and there are experimental evidences of these arcs with a scientist from Bangladesh, experimental from. So, if you have connections to this country, maybe it's your destiny to work on wild heavy metals. And there is a discussion of how conductivity can change abruptly in the materials with this cone-like dispersion relations. Okay, I'm done. David, do not take example from me. For second year seminar, one should do much more thorough and higher quality review of literature. I wouldn't deserve any good grade. So invest time. So what can we do at our side to maybe approach this area? So on one hand, if it is one point and there is just without any expertise in this area, one point in the dispersion space, there is no chance that charge carriers will stay at a point. There are dynamical processes that accelerate, decelerate. So typical thing is to look if there will be some motion in the vicinity of this point, if in the phase space, on one hand. On another hand, if there is no resistance, if currents can persist for a long time, most typically are not linear currents but circular that are created by changing magnetic fields, as done in levitation experiments for superconductors. So if we want to adjust our suite of codes for electron dynamics toward these effects, we do need two key features. One that is being developed by Fatima for explicit inclusion of momentum, direct and indirect transitions. And second, explicit inclusion of magnetic field, which is a source of circular motion. In this aspect, there is a niche in the community. So because of objective difficulties, so magnetic field is not challenging itself. It's part of the 300 level courses for electrostatics. But if one wants to combine magnetic field with electronic structure calculations, it is objective challenge not in theory but in how to implement it. So magnetic fields coexist with currents, with charge density moving. I know that we are describing motion of charge densities, but typically we are looking for like transition from donor to acceptor rather than continuous currents. And in presence of magnetic field, a changing magnetic field, there are persistent currents, charge densities, and they affect electronic structure. So one does, in order to naturally include magnetic fields, one needs replace, like even if we do not go beyond above DFT, so density functional theory. Instead of density, one needs to use current density, C DFT. And then current can go in any of three directions, so there are more components. And for electric magnetic fields also there are components, so it's just more heavier object than regular DFT. And one day there will be software written by someone for public use, but it's not available today. So, and making universal software, it's too hard for a small group. It needs like big institution. But we can make a shortcut and combine outcome of regular DFT with some homegrown simple scripts that will mimic effect of magnetic field. So if we are looking on planar materials, then magnetic field is bundles with angular momentum, right? That composed of mixing of position of momentum along different directions. And the same thing can be done for in momentum space. Why we need momentum space? What is the reason? What is the benefit? If we go into coordinate space, things are a little easier and more intuitive there. But then if we want to import the specifics of material, then one needs potential. And potential is defined in too many points. And it is potential for one electron, while we are describing many electron problems. So it will be, it's pity that London is not here, but you saw from his works that he did before starting DFT that just David did this too, right? Importing log-pot potential from VASP and trying to find eigenstates in that. They are maybe qualitative, somewhat similar to reality, but they will be never close in quantitative values. So it is extremely rough approximation. But if we are going to consider everything in momentum space, one can import, one can use already diagonalized information about dispersion. So energy as not as function of position, not potential energy, but energy as function of k points. And they are higher order information that includes all interactions. In software that we use in VASP, the k points are integrated part, and we can just use the momentum dispersion as grid points and in this space of momentum to explore dynamics in a similar way as Fatima was doing for one-dimensional nanowires. But here it will be more points because it will be 2 dimensions. Like if there were 4 in one, 4 in another, it's 16. And to have the circular motion, maybe instead of 4 by 4, it should be like 50 by 50, something like that. Which is a little scary for big materials, but if it is graphene, if it is smaller unit cell, it should be possible. So, did anyone try to run this code that was shared? It's fine. So we all are practicing for a long time one-dimensional wave packet dynamics, and it's not a big problem to add second dimension. If there is no coupling between motion in 2 dimensions, it's almost evident. The only thing is to add, if we need circular motion, then one needs to couple motion in x and y. So this slide shows preliminary results of 2-dimensional dynamics in 2-dimensional free space. Why 2-dimensional free spaces? we may want to combine many things which is too ambitious. Two-dimensional things, circular currents due to magnetic field, and the features, electronic structure features specific for each material, and later on the dissipative processes due to interaction with photons. Everything at once is a little scary. It's better to divide and conquer and debug little things first. So here are two dimensions. Initial wave packet in each of these panels is the same, and those are isocontours. Same as we plot orbitals with isosurfaces, like three-dimensional object is represented by surface. Isocontour is when two-dimensional object is represented by line, right? So it's a value when wave packet has certain height. We should interpret it as little Gaussian in both x and y. I'm not a good painter, but it's a little hump here. And the panels differ, they are the same with the initial condition. This initial wave packet has non-zero momentum in both x and y. And the difference between panels is different values of this model magnetic field that is implemented with angular momentum and dipole interaction. So if the magnetic field is small, then the wave packet does two things, two-dimensional wave packet. It moves linearly forward according to, by inertia, according to initial momentum, and it slightly expands due to Werner-Heisenberg uncertainty. In free space, the width of electron increases. If one adds magnetic field of different value, then by this Lorentz force, it starts curling. And the larger the value of magnetic field, the shorter is radius of curvature, so it makes more and more sharp turn. It's like driving straight and then turn. And also it speeds up, the motion becomes quicker, so magnetic field accelerates. It does, the energy is conserved, but if you have the same kinetic energy and you move on the lower orbit, like if ballistic missile, well, something peaceful. If a satellite needs to be deployed and burnt in the atmosphere, when it comes closer, it goes quicker and quicker. And those are snapshots. Those isocontours are made at each step, and there are trajectories. So if magnetic field is high enough, it's like 0.3 in some atomic or arbitrary units, it makes a full circle. So it's persistent current, energy is conserved, but it moves constantly. So this is the same thing. So it's motion of the wave packet in x and y, and in presence of magnetic field, it makes curved motion. So here is a slightly different initial conditions, initial momentum and value of magnetic field. Therefore, the combination of linear motion, expansion, and this curving due to magnetic field contributes, and it loses its nice shape very close, but soon enough it will be represented as set of circular orbits of different radius, which are solution eigenstates for this Hamiltonian, and those are Landau states. Oh, I should include this in the page as well. So it goes around. If one reproduces the same simulation in momentum space, if you are doing it in a free space, there is no way, no need to draw potential, because in free space potential is zero, and magnetic field is not conservative. You do not represent it with the potential, right? It's you just represent it mathematically. Otherwise, it will be infinite spiral that makes you go down. It's something that is not typically visualized. But if you are doing it in momentum, so it's momentum along x and y, then kinetic energy is square of momentum, right? It's a parabola. And if in momentum space, if we do not have, if magnetic field is zero, then momentum is conserved. The packet will not move anywhere. But if we launch magnetic field, this wave packet will start changing shape in some way. I don't know if it is truly so, or maybe there are some bugs to debug. And this shows kinetic energy, so it's swings between kinetic and magnetic part of energy, and initial wave packet distributes. What is interesting, it doesn't go too far away from initial area, so its total energy is expected to be conserved. And these two animations are connected. So ideally, when it is expected that both position space and momentum space, there will be circular motion of this two-dimensional wave packets. I don't know what is better here. I think it is the same thing. Just in the removing the potential and looking onto distribution and momentum. The to avoid errors on the borders, one needs to take broader range. And, it's yet to be checked and debugged, but right now the main goal is to set up skeleton that is potentially a good thing for competitive proposal. So these previous figures were dealing with free space, with no atoms, no potentials, only magnetic field and kinetic energy. But the keyword is quantum materials, so it's something real. And here are, it is something I did this morning with a debug queue for half an hour, so it's not very high precision. So it's 8 by 8 grid points, and it's a little larger than single unit cell. It's like 8 carbons, two-dimensional supercell, and here are energies of frontier orbitals, HOMO and LUMO, as function of momentum in x and y. I don't know why on textbooks and in Wikipedia there should be 6 Dirac points. Here I see only 2. So it's this is not yet competitive figure. Maybe if one the unit cell should be hexagonal and it should have only 2 elements. And this, if one increases size of unit cell, maybe there are some additional effects. And spacing of these grid points is not sufficient. Is like 8 by 8, while for the free space simulation on previous slides it was like 50 by 50. So in order to import, so the idea is to import energies of all these points from electronic calculation and place them here. so that motion of wave packet will experience this dependence of kinetic energy of momentum, which is different from free space, and will already include all features of materials, right? And then include the magnetic field in the same way as we did before. And what will come out is unknown. Or maybe if one looks through multitude of theory and experiment paper, maybe there will be some hints. But before we had wave packet motion around center of parabola. Here I do not have intuition to tell what will be the motion of wave packet. Will it be around this Dirac points? Will it be somewhere else? So it's an open question. And it could be, I want to hope that it is something competitive to offer to agency. So this is something that can be completed relatively quick and can be applied with minimalistic effort of debugging, and can be applied to a range of two-dimensional materials. Like if one takes the materials that David is exploring, unit cells are a little bigger, and making 50 by 50 key points could take longer time, but in principle it is only single point calculation. For this part, for electron dynamics that doesn't dissipate energy, for energy conserving dynamics, even with magnetic field, numerical expense is cheap. And it can be applied in a short time to a range of materials. But what, and this can be done probably by anyone in the world pretty soon. So this is time-sensitive thing. But how to, is it possible to combine these features with major strengths of several computational chemistry group at this university to description of the non-radiative relaxation? All these exotic properties are typically explored at liquid helium temperature, because at high temperature all these nice features are suppressed. But at which degree are they suppressed? Can we determine temperature, maximal temperature at which useful effects like this circular currents will still exist? So if one redo these calculations along nuclear trajectory, then it will be super expensive. Instead of one calculation, 50 by 50 K points, it will be like 50 by 50 by 1000. So it's very ambitious. So highly likely energies of at each K point will move. So it will be like breathing dispersion curve. And due to nuclear motion, the states will be not orthogonal to each other. There will be transitions both to other bands and inside one band with dissipated transitions that are not like here. Magnetic field induced transitions do conserve energy. Typically they go on the tangential line. And if one would include non-radiative relaxation, they would go either to the center or to the nearest minimum, and they will dissipate energy away and stop this circular current. This could be very valuable to assess the strengths of specific material if these non-usual effects will be possible to observe at room temperature, or at least something a little higher than helium. And here are results from Fatima. They are one-dimensional, but there is momentum and energy. And it changes, the wave packet changes both expectation value of momentum, expectation value of energy, and fluorescence. The goal, if one wants to pursue this research direction, is to generate the same type of data, same type of dynamics where momentum will be not one-dimensional but two-dimensional. So it will be like surface for occupied orbital, surface for unoccupied orbitals, and wave packet will depend on momentum along x, momentum along y, and energy. So it will be like object that will move in 3 dimensions. And in presence, like at low temperature, relaxation will be very slow, and wave packets will be able to perform circular motions. At higher temperature, they will relax to a terminal point and sit there no matter how strong magnetic field is. And these features will be different for different materials, and it will be a positive outcome of the research if it is completed. So, free space in position, free space in momentum, the magnetic field induced motion in realistic electronic structure based dispersion curves, and then combining this magnetic field induced circular motion with non-radiative transitions due to non-adiabatic dynamics. And maybe one can also later on, by now it's more than enough, but one can also bring electric field and see response, like will this circular currents be responsive for electric field perturbation? Could it move continuously across the sample or conductivity? Okay, let's send. I'm done. It would be really great if anyone has a discussion point.
I have one, not question, I just wondering, they are talking about the well arc, but in this graphene is like a circle, like, because of symmetry. So what is the significance of this arc and symmetry?
I know as much as you do,
Oh,
or less. So the necessity is to, well, I was just scanning through, and it looks like it is important to jump from one Dirac point to another Dirac point. Like electronic motion in the vicinity of Dirac point doesn't have friction, another no friction, but will there be losses while moving from one to another? And there are some novelties about probably lossless transition from one point to another. I don't know if it answers anything, but it's the impression that I've got while scanning through. Okay, floor is yours.
Okay, hi everyone, I'm Kevin, and today I'm going to be talking about the progress I've made so far for my research project. Okay, so basically the goal is to calculate the charge transfer rates for two models, interface 111 and interface 100. And this project is basically a spin-off from the Chemistry 676 class project I did last semester. If you guys remember, in the project last semester, I looked at 6 models. 4 of them, 2 of them were doped with sodium, 2 of them were doped with iodine, and 2 of them were not really doped. So the basic goal for that one was to see which PBTE nanowire what was the best. And this is the same thing here. I'm looking at the charge transfer rate for both of these models, and I'm trying to see which interface would be the best. Okay, so the methodology for this is as follows. Basically, the first step would be to calculate the couplings for both interfaces. The first step would be to perform heating computations for both of them, and the second one would be to do molecular dynamics for both of them, and then finally I have to perform coupling calculations for both of them, and then after that I use the MATLAB code to calculate electron dynamics and charge transfer rates. Okay, so this is all the progress I've had so far. All couplings for interface 100 have been computed. I'm in the process of calculating charge transfer rates using MATLAB code. I have to learn more about how the MATLAB code works, mainly what the MATLAB code says and how to modify it. So I have to do that by talking more with you guys, such as Yulin and the professor. And then for interface 111, the heating and molecular dynamics have been computed. And I'm in the process of computing the couplings for interface 111. And for that, I have to learn how to modify the Voss code. When I'm trying to compute the couplings, I'm getting some sort of error messages. So currently, I'm trying to consult with people to learn how to get past that and to get the coupling files needed.
But as soon as couplings are ready, you the rest of process is easy for you,
Mm-hmm.
right?
Mm-hmm. Okay, and here are some of the preliminary results that I have. This is a position versus time graph that I have for interface 111. On the y-axis, we have the electron position, and on the x-axis is time. So this is just a preliminary result that I have for that.
Wait, what are the colors? What is the definition of color codes? What's the difference between blue and yellow?
let's see. If I remember correctly, yellow is an electron hole, or
Electron.
yeah,
And blue?
blue is the hole.
Mm-hmm.
All right.
So what do you see with, if you accept this definition? What do you see on how do you interpret this figure?
Okay. For the positive times over here, I guess at electron distance -10, there seems to be some sort of electron movement here.
Why at initial point of time electron and hole are located in different areas of space? And how do you create, what are your initial conditions? Like if the system is initially in ground state, there will be no dynamics, right?
Right.
So you do something, you perturb it away from ground state. So what do you do? How does initial state differs from the ground state?
So in the initial state, there's no movement, there's no perturbation, but then as time progresses, you introduce some light, so then the system perturbs into a higher state, right?
Yes, very good. But can you add a little bit more specifics? What does it mean, higher state? Like if you have occupied orbitals, unoccupied orbitals, like orbitals with electrons, orbitals without electrons, and then you have light. What happens after?
It's the electrons' energies changes from a ground state energy to a higher state energy.
Well, it's too global, but more mechanistic details. Does it take electrons from occupied orbitals? How many electrons? What happens?
So basically, from what I understand, the electron jumps from its ground state orbital to higher orbitals that were
Good. Just terminology from one of the occupied orbitals to one of the unoccupied orbitals, right?
Mm-hmm.
How does electron know from which orbital to which orbital it will jump?
How does electron know from which orbital to which orbital?
Mm-hmm. Like if electron is sitting on HOMO -10,
Mm-hmm.
does it know if the electron wants to jump to LUMO or LUMO plus 100?
Okay, so the way I understand it is that LUMO -10 has a certain energy associated with it, and the regular LUMO state has an energy to it. You take the energy for each of those states, subtract them, and then that's the difference in energy. So if the electron is LUMO -10, it'll need that difference between those two energy chains to jump to that higher energy.
So it needs to be in resonance with frequency of light.
Mm-hmm.
So those pairs of orbitals which are in resonance with light will be perturbed by this light, right?
Yeah.
Yeah. So you may want to like type it or explain it next time.
All right.
Good. So your initial state is a pair of occupied and unoccupied orbitals which are localized not in the same areas. Is your sample homogeneous? Which material do you are telling interface 100, but what is the material that you are studying? Is it like silicon or carbon nanotube or?
It's a PBTE nanowire.
Okay. Is it all atoms are lead and telluride?
No, it's they're doped.
Okay. So please next time mention it because each talk is assumed as like fresh
Okay.
to ignorant audience.
All right.
Give all the audience.
So I should assume no one has like any prior knowledge.
Exactly. Exactly. It's rules of the game.
Okay. Okay, and then my final here is a three-dimensional graph. On the x-axis is my orbital index. On my y-axis also has an orbital index, and then on the z-axis is a position.
What? Position? Position of what?
Position of the electron. No, wait. I misread this. This is a frequency because it's seconds in inverse.
Okay, frequency. Frequency of what?
Frequency of that light photon that the electron absorbs to jump into the unoccupied orbitals.
Not very far, but not correct. A little different. So, can you go one slide back? So, why electron and hole are moving in space and in energy? We apply light only at the initial time, and then we switch like light, and then we put it in a dark room. No light, and then it still moves somewhere. Why? What is the reason why electron and hole are moving in energy and in space?
Because when the light was on, it absorbed some energy from the photons around it, and then when we turn the lights off, the energy didn't go anywhere. The electrons still have that energy within it, so you'd expect for there to be some movement.
No. If the electron is in the eigenstate, it has some distribution in space that doesn't change. If we believe in quantum mechanics, then eigenstate doesn't change in time, right? So if you promote system into one of its eigenstates, there will be no motion. Energy will not change and position will not change. It will be some distribution but without motion. And you see drastical motion. Your electron and hole move by 3 nanometers, 30 angstrom. What is the physical reason for them to move? Which process you are hiding from us?
The thermoelectric effect.
Later, it's connected, but at lower level, basic, very basic process. So you do have your electronic states before you had a light that interacts with electronic states. What else exists in nature? What is the temperature of your? You mentioned you do molecular dynamics at you're heating to certain temperature. Molecular dynamics and couplings. So what do they reflect? Which interaction they help to describe?
They help to describe how electrons interact with each other.
You do not need to heat sample. In ground state, electrons will interact with each other. It's a natural feature of any electronic structure theory. Why do you heat your model? When you heat, what does it mean, heat?
That means you're adding thermal energy to a material.
And what happens to nuclei, to atoms?
So in lower temperatures, it vibrates, and then when you add heat to it, it vibrates faster and faster. And then when you add enough energy, the
maybe not
electrons
faster, larger amplitude.
Okay.
But yeah, yes, good. And how nuclear vibrations affect electronic states? Do
it-
nuclear motion affect? Does nuclear motion affect electronic state?
Yeah, yes, they do affect the electronic states.
Good. Please continue.
Okay, so uh, if the nuclei had lower vibrational frequencies, then the electrons orbiting them will be in the lower ground state orbitals. But then if the nuclei were vibrating at a higher frequency, then the electrons surrounding it wouldn't be in the ground state orbitals anymore.
Well, right now you're telling a story about thermoelectric effect itself. It's more complicated, and we are looking on a basic, like if there are two electronic orbitals,
Mm-hmm.
and there is a energy, same as you were describing photons. If there are two electronic states, and there is a photon that is in resonance condition, then photon may induce electronic transition, or electronic transition may induce emission of a photon.
All right.
Right?
Mm-hmm.
Same with atomic vibrations. If the frequency of atomic vibrations is equal to the energy offset between two electronic states, then it can either induce absorption of energy from thermal to electronic, or there can be release, so from higher energy state to lower energy state.
All right.
And energy is dissipating into nuclear vibration. So we are not showing it in simulations, but we imply it in our heads that when this motion happens, sample is getting hot.
Okay.
It releases energy from electronic excitations to thermal vibrations.
All right.
Therefore, it changes energy, and both migrates in space. Make sense?
Mm-hmm.
Okay, so let's go to the slide where we stopped. So what are those frequencies?
So the z-axis is the frequency of the nuclei vibrating.
Not quite. Your first guess was that it is frequency how efficient electrons are moving from one orbital to another due to light.
Mm-hmm.
Repeat the same and replace light with nuclear vibrations. So just say it yourself.
Okay, so it's basically how electrons. It's the frequency at which electrons vibrate.
Rates. How quick electron goes from one orbital to another one
All right.
due to release of heat into vibration of atoms.
All right.
Okay?
Mm-hmm.
So this is two-dimensional object, matrix. There are index on X, index on Y. And each, skyscraper, which can be either tall or low, shows it has two indices, I and J. So if it is tall, it means from I to J it goes very efficiently. If it is low, it means from I to J it will not go.
Okay.
So some states will cool down quicker, some will cool down slower.
All right.
If it is the last slide, you may verbalize your conclusions or open questions that you want to address.
All right. And that's it for my talk. Are there any questions?
No.
Wait.
Summarize. Conclusions.
Okay, so in conclusion, I've just talked about my research and my progress thereof. Namely, I'm trying to calculate the charge transfer rates for two models. I've computed the couplings for one of the models. I'm having difficulty with the other, and I've just talked about. And I've just demonstrated two figures that I've gotten from my research. Are there any questions?
Oh, let's thank Kevin for the effort. I do have questions.
Okay.
So let's go to your second from the last. Second from the last. Just go to the end.
6, I guess.
Yeah, this one. So, what are your plans? Do you plan to repeat this calculation for the same model again and again? Is there a reason to repeat calculation of this figure? Am I saying something silly, or it is, or there is a reason to repeat this calculation again and again?
Okay, so as I understand it, you want to repeat this calculation again and again for different couplings.
No, different couplings will be also very interesting, but it is expensive. With different, what else can you change?
With different initial conditions.
Exactly, exactly. This is like 2 minutes per each run. In one night you can accumulate data for a paper.
Okay.
And I hope you figure it out, but you can do it by next time.
Okay.
So just, do you remember which parameters in the code you need to update if you change your initial conditions? Which variables? Ask help from the club. Everyone knows here.
All right. So I guess my initial energy and position.
Which variable? There are like 2 variables at the beginning of the code that you change manually. Look around, maybe someone wants to help you.
All right.
Check if David wants.
I don't remember what they are off the top of my head. It's I hole or I electron or IE, IH, something like that. I'd have to look at the code to find what the variable exactly is, though.
Yep, yeah, exactly. And what do they mean? Like,
The initial position of the electron and the initial position of the hole. So
do not use word position. It's very confusing, especially for people with physics background. Like position is coordinate in space.
So it's the initial level.
Okay. Yes.
So if you have IE equaling 10, it would put the electron in LUMO plus 9.
Mm-hmm.
Because LUMO would be 1, HOMO would be 1, and then you're just adding on top of that or subtracting for HOMO.
Excellent. Yeah. So you just take the code, change these 2 variables.
Mm-hmm.
Right now they something like from HOMO minus 20 to HOMO plus 30, and change them by 1 and run again and record figure and numbers that comes out.
Okay.
And just by analyzing this data, you will learn something interesting and new, and it will be sufficient for a little paper.
Okay.
It will be both interesting for you, useful for community, and easy to do.
Got it.
More questions?
Maybe you already have mentioned it. What is this solid and dotted line?
Okay, so the solid line is the electron itself, and the dashed line is the electron hole.
Is that average?
Just whole, absence of electron. You
Okay.
wanted to say, right?
What is average energy?
Expectation value.
Oh, okay.
But it's not
But-
it's not energy, it's position.
It's position, right? But I'm just confused because of this blue line and green line. Green space is above and below this line.
Just by procedure, expectation value has only one value at each time. There is no forking here, even if
Oh, so this is the.
it's not the maximum of the peak. It's just expectation value,
Oh, okay.
like center of the distribution.
But yeah, that's make me confused. But because it seems like most of the population is around like -40, -50, that region. How is that average position of the expectation below is around 10? Around
There could be something near +50, but for human vision, there could be interference between orange and blue clouds.
Oh,
They
yeah.
kind of masking each other.
Oh,
It's more correct to do separate electrons and holes, but then it takes twice as more space and harder to analyze, and it's waste of space and figures.
but yellow is then highest in a scale, maybe color scale, right?
Mm-hmm. It goes from dark blue to orange,
Orange, yeah, orange.
and one can normalize it so that neutral will be green, but maybe this normalization procedure was not taken care of in this specific case.
Yeah, but after the relaxation, after the like 1 or 10 picosecond, it look like it's localized on a very narrow region, like very bright
Mm-hmm.
orange region. But the average line is still way above and is slowly down.
It doesn't surprise me.
Yeah, that's-
In doped materials, the orbitals are not localized on doping atom, but typically take nearest neighbors.
mm.
So, supporting discussion. Anyone wants to learn something from Kevin?
So another thing is, I don't remember actually your actual system because you already mentioned that you showed that as before, but I forget that. So since it's interesting that it's flipping their localized position, how is your system look like? I mean,
Just
That's
explain by words or by hand waving what your system is.
how is your system look like? I don't remember exactly that.
You mean how what the nanowires look like?
Mm-hmm.
Yeah, I mean, how is their geometrical feature something?
Okay. One is a pure cylindrical shape,
Mm-hmm.
and the other is more of a, how do I describe it? Helical ish shape. I don't know how to like describe the shape of that system. Yeah, I should have put a picture up here.
So it also has symmetric in the z-axis?
Yeah, all my models are symmetric on the z-axis.
Oh.
How many atoms is in your system? Well, it's hard. No one is expected to remember, but roughly, is it like 5, 10, 100, 1,000, maybe 200, maybe 300? Approximately, what's your last number?
Hundreds.
Okay, a couple hundreds.
Mm-hmm.
And how close or how far lead and what is the stoichiometry? Is it like lead 2 telluride 3, or it is 1-to-1 ratio?
1-to-1.
Okay.
So it's about 100 atoms in like 9 nanometer thickness?
So how far is one lead from 1 telluride? What's the interatomic distance? Roughly, do not...
I'd say about 1 or 2 angstroms.
But 1 or 2, because Jebet is asking, is curious, typically for hydrocarbons or for carbon-based materials, the carbon-carbon distance is like 1.4, 1.5.
Mm-hmm.
And if you assume that your several hundred atoms have 1.5 interatomic distance, then the length of your nanowire will be maybe like 30 angstrom.
All right.
And if it is almost 100, it should correlate to the either you have very thin nanowire or interatomic distance is substantially bigger. It's maybe like 3 or 4 angstrom. Do you remember something like this? not now,
Oh.
but you may check
All right.
because it's not usual for conventional materials on one hand, but on another hand, those are heavy elements with large ionic radius, and it is not a big surprise that interatomic distance is a little bigger.
All right.
This is not a discovery, but it's interesting technical information that some experts could be interested in.
So I'm just curious because what is confined in X and Y directions? What is the longest dimension? Z is the longest dimension in your system?
Yeah.
You're saying the nanowire is because one dimension is comparatively longer compared to other two.
Yeah. The Z dimension is definitely
Is the
longer.
longest.
Yeah.
So it should be Z direction. It should be periodic in that case.
Exactly.
Then what is the significance of this figure? Because it plotted it to the Z projected in Z axis.
Ask Kevin
Oh,
a question that he was already answering.
no, it's not actually a
Ask him-
question. I'm just
no, no,
wondering. Yeah, I'm
for
curious.
learning, not to check his knowledge, but for your curiosity.
Yeah.
Ask him if the system is homogeneous. Are all atoms lead and telluride, or there are any impurities?
Oh.
No, no, ask him and listen
So-
to it.
There are some impurities in there. But both the models I'm studying have been doped.
Oh, so they have some impurities in Z direction. So that's why it's also important to look on the localization in Z axis, although it's periodic. So what is the length of X and Y axis? I just want getting some idea about your system here. So it seems like your Z axis is about 190 or 100 angstrom.
Mm-hmm.
How long is your X and Y axis?
What's the diameter?
What is the diameter in other cases?
If your nanowire is cylindrical, what is the diameter? What is aspect ratio? Roughly. It's,
Roughly, not exactly. I'm just
is
trying
it,
to
like,
get some
is it
idea
like 1
what
to
it
2
is.
or 1 to 100 or 1 to 10?
Oh, you mean the ratio of the X and Y axis compared to the Z?
Oh,
axis?
Yes,
Z axis,
yes.
yeah.
Alright, I'm gonna
Just
suggest-
visually, you can remember. Like,
What?
maybe in your memories you remember how it looks like. and-
maybe 1 to 50, 1 to 60. That'd be my rough guess.
A little less ambitious, maybe 1 to 20.
100.
Any other questions?
So, which model specifically is this? You say you have
Uh,
different doped and non-doped,
This is for the Interface 100.
but is this model one of the doped models you were looking at, or
You mean like?
you said you had iodine doped, non-doped, and
That was
Third
that was
dopant
for
that I
my
know.
class project. Here I'm looking at two somewhat similar but different models.
So to save time, instead of doing meticulous screening of all possible versions of the material, he's looking on most important, when there are both doping simultaneously,
okay.
and they are responsible for this vivid charge transfer. Without doping, it will be like boring, homogeneous, like the whole figure will be like homogeneous color
Yeah.
without any change.
What's the meaning of interface here? Because usually when you have interface, that means you have two different materials, right? And they just touch with each other, so you have interface. So what's the meaning of interface here?
When you're saying 111 and 100 here, what is the difference in your system in these two cases?
Are they doped differently, or they are oriented in space differently? Like, good question.
Okay, so from what I'm guessing, so the 100 and the 111, it's referring to their shapes, how they're shaped differently. So in response to your earlier question, I said one of the configurations was purely cylindrical shape, and the other one was somewhat helical shape. So the 111 and the 100 is referring to that.
Which direction is nanowire is growing? Is that so? It's not a doping.
The index 100 and 111 doesn't relate to doping. It relates
It's a
to,
growing.
and the best expert to help in this question is Fatima. She's publishing papers on nanowires grown in different directions. So she probably is best educated of all of us how to explain what is this, what are those indices.
Any other questions?
I have a question. Why these exponential fitting lines overlapping, like crossing? Is it?
All right. Sorry, can you repeat your
There are
question?
two exponential fitting lines for electron and hole, right? Why they are crossing?
Why these two lines are crossing?
Mm-hmm.
Look on their position of initial and final states.
Okay, so here's the yellow line. This fate yellow line here is the position of the electron. As you can see that as time changes, the position of the electron changes from here to there.
If you're not satisfied, keep asking him. That's his
I
responsibility.
know the electron should be relaxed at the LOMO and hole should be.
Here is
This
position.
is
What is your
the
axis?
yeah.
How your label axes are labeled? What is your y-axis?
My y-axis is in interatomic distance.
Is it introduced?
Coordinate, position.
Okay.
But some of us from previous practice may think that your y-axis is energy.
Okay.
Can you certify that it is not energy but position?
Yes, it's not energy; it's position.
Good. More questions? Okay, if no, let's thank Kevin once again. Maybe it's not a bad idea to have only like couple of figures. Then everyone has time to like think and develop questions. Because if there are like 50 figures, there is no time to focus and discuss. Good, good. So, on coming Friday, there will be merged meeting with Dr. Kilner group, although she's on travel, and there will be likely Levi will present, and David will make a practice talk for his second year seminar.
There have a chance maybe Levi going to miss that talk because he will be flying that time.
He will miss his own talk
I don't
or
have
talk
you
with
know,
David?
his own talk. I mean, he couldn't join anything. I am not certain yet.
Okay,
I will-
then we will have more chances to ask more questions to David. Which
I will confirm.
which is beneficial. You suffer more on.
I know it's beneficial. It doesn't seem like it though.
No, you will excel on the formal presentation.
When is your presentation?
September 23rd.
He's number 2,
Yeah.
almost the first. And there is when semester starts, there will be no time to practice. So basically, it's your major practice on Friday.
I chose an early date,
Huh? Day of Glory?
because it was the last one left.
Oh, yeah.
Is there, do you have any presentations for next Tuesday? Anyone volunteers, or it's up in the air? Okay, we can decide it privately. If there will be no urgent things, we will postpone. Or, I will fill the gap in the same way as today. Okay, so this grants activity is very free will volunteering. If you find some of ideas useful, you're welcome to use it for your own personal benefit, like Kevin and David may consider to submit an SF, GRFP, and you can either mention what you are already doing or borrow some ideas from what we discuss here or design something personal. But it's worth of trying. Like two pages of text, definitely worth of 3 years time. I'll probably ask some of you in person to help in preparing write-ups of what we discussed. So just maybe write a paragraph of your feedback or your ideas about this materials and key points. So if we bring it together and edit and send, everyone in the group will benefit. And if it will lead to no success, it will be a good practice, because if you plan for a career or into academics, it's an activity that needs to be done again and again. Okay, well, many thanks for investing your time.
You decided.
Meeting is dismissed, and I'll stay here a little longer just for one-to-one brief chatting.
Have you decided your topic?
Yeah.
What's that?
The holiday.
Oh, by the way,
It's very simple.
Yeah, they,
What
now
day?
they changed the rules. Now we can present.
Yeah, I
It's
got
gonna be
your
very similar
email
to Daniel's.
and